All right, so far we've been talking about populations in general, but now we're going to focus in on how human populations have changed over time and some of the factors that affect how human populations change. By the way, in case the news hadn't reached you, the world's population officially reached 8 billion people within the past couple of years, and it's still growing. So, some of the factors that affect how human populations grow are very similar to the factors that affect how other populations grow. We are organisms. Some of the same rules apply. So, birth rates, aka natality, are going to affect how populations grow, as are death rates, mortality. But an additional factor that's important is infant mortality rates, which we'll talk about on another slide, but it's essentially how many children that are born die before they reach the age of 1. These are some of the factors now that are different for humans than for other organisms. So, access to family planning resources, a nutrition level, especially when the children are young and growing up, the level of education, especially of women, and the age at which people are married. So, this is the general equation that you use to calculate the growth rate of a population. And I'm going to talk about each of the variables. So, the growth rate as a decimal here is R. N is the starting population. B equals births, I equals immigrants, D is deaths, and E is emigrants. And you'll notice that they're kind of clustered together so that you have the number of individuals entering the population minus the number of individuals leaving the population. And it's kind of weird, but my trick for remembering this equation, because you will have to memorize this for the AP test, you do not get a formula chart, is to remember Biden. Should be fairly easy. He is our current president. You just have to remember it's Bide over N. I don't know if that's helpful for you, but we'll see if that helps. All right, so we're going to have sample problems with each of the equations we go over. We'll also practice this math in class. Populations math is not super difficult, so it's a matter of memorizing the equations. So we have a population of wolves that has 25 births, 10 deaths, 5 immigrants, and 10 emigrants to this population, which started out with a population of 50. So what was the growth rate? So it's going to be births plus immigrants quantity minus deaths plus emigrants, all divided by n, which is our starting population. And that's going to give us R. So if we plug in these numbers, it's going to be 25 births plus 5 immigrants minus the quantity of 10 deaths plus 10 emigrants, all over the starting population of 50. If you do that, the number you get is 0.2. So remember, this is calculating your growth rate as a decimal. If you want to convert this to a percent, you're going to take this and you're going to multiply it by 100%, which would give you a 20% growth rate. Keep in mind that you have to remember which formulas are going to give you growth rate as a percent or involve growth rate as a percent versus which ones involve growth rate as a decimal. All right, some other calculations that we can make are the crude birth or death rate. The formula for them is going to be very similar because you're calculating the number of each of these events, birth or death, in a population per 1,000 people. So this kind of eliminates looking at it in a large country versus a small country. You can kind of compare the births uh, per every 1,000 people. So crude birth rate, or CBR, is the number of births in a population for every 1,000 people. And that's the formula right there, where again, N is the population. This is another equation you have to memorize for the AP test. Sorry, if they change the AP test sometime soon, we'll lobby for a formula chart. But until now, you've just got to memorize it. All right, crude death rate, or CDR, is the same, except it's the number of deaths in the population per 1,000 people. So let's do a sample problem now. We have a city that has a population of 10,300,000 and it had 3,400 births last year. So we want to know what is the crude birth rate. So CBR is going to be the births divided by the population, or N, times 1,000. That's going to be 3,400 divided by 10,300,000 times 1,000. And if you calculate that out, you'll get point, sorry, 0.33 births for every 1,000 people. So notice that number can be less than 1 because you're not saying a third of a baby was being born. You're saying that for every 1,000 people there was, a 0.33 births. This would mean that you'd have 1 birth per every 3,000 people, essentially. So, like we've talked about, factors that affect human population growth can be very similar to those that affect other organisms' population growth rates. You've got density independent factors, a lot of weather related things like storms, fires, heat waves, or droughts, which can increase death rate. And then you have density dependent factors, things like access to clean water and air, the food availability, disease transmission, and territory size. And since these are density dependent, all of the effects of these tend to increase as population density increases as well. So just to look at the historic growth and population of the world, this is a graph estimating for the past 12,000 years or so how the human population has grown. Now keep in mind, everything before recorded history is an estimate based on kind of archaeological evidence. But for most of the for most of the history of humanity, our population has been well under a billion. In fact, we didn't reach 500,000,000 people until probably close to like the 1500s or so, because we reached it just after the Black Death pandemic. So notice our population has been increasing. The only time you can really see a dip in the population was when the Black Death killed like a, you know, large chunk of Europe's population. It killed about 200 million people. Other than that, the population growth has been increasing. Now, notice that at around this point, population growth increases exponentially, and we start seeing a massive increase in the population. This is due to the Industrial Revolution. And if you're wondering why the population increased so dramatically at that point, we're going to talk about it when we talk about the demographic transition model. So just notice that the amount of time it's taken to add 1 billion people to the population has decreased dramatically. So we reached 1 billion people after 1800, right? In 1928, we had 2 billion. In 1960, we added another billion. In 1975, we added another billion. In 1987, I was about 5 years old. We had 4 billion people. Within my lifetime alone, I have seen 3 billion people added to the population. So that's quite a massive growth of population. Population is, we kind of say it's population growth is limited by what we call this Malthusian theory of population growth. There was this guy, a philosopher named Thomas Malthus. He actually influenced Darwin's theory of evolution. He said that populations increase exponentially. So if you look at this graph, the red line is population, and it's increasing exponentially, faster and faster and faster. But resources only increase linearly. So you can add more resources, but it's not going to increase as fast as the population increases. So eventually, at this point of crisis, you reach a point where the population is higher than what the resources can support. And this is, by the way, our carrying capacity. And then you have a population dieback. You have an increase in death rate, a decrease in birth rate, and the population decreases and the growth rate decreases as well. So if you ever see a reference to Malthusian theory, this is what it's talking about. Now we've got another equation. This should be one of the last ones that we have for populations. We may have one or two more later on if I determine that these are going to be ones that you need to memorize for the test. This one you do need to memorize, and it is doubling time, also known as the rule of 70, and it's the number of years it takes to double a population. By the way, There is an R in this equation, but R is the growth rate as a percent. And so we're going to do a practice problem with this. We're going to say that we are looking at Madagascar and its population growth rate is 3.2%. So R is going to be 3.2. How many years will it take for the population to double? Well, doubling time is 70 divided by R, which is going to be 70 divided by 3.2. And that will be 21.9 years. So what that means is that every 21.9 years, if the population growth rate of Madagascar stays the same, the population will double. And that is a frequently asked calculation, so yes, you definitely have to memorize this equation. By the way, I know our population as humans has exploded dramatically, but actually, if you look at it from about 1960, 2 or 3 onward, our world's growth rate, population growth rate, peaked. It was at 2.2% at that point, and it has been decreasing ever since. And the predicted trend from about this graph was made in, I think, about 2015. So the predicted growth rate of the population is going to keep decreasing. Unfortunately, we have so many people that even with the slow population growth rate, we'll still keep adding quite a few. There are some projections saying that by 2100, we're likely to reach 10 billion people on the planet. And that's a conservative estimate. We might reach as high as 12 billion. All right, so we've got one more lesson coming out tonight, and I'll go get to that.